All right, let's see how you did on your basic probability. So on this first problem, when I'm reading it, I can tell that I've got some things that happen, the statistics circle and then the computer circle, but I've got 7% who have done both. Okay, so when it says 52%, that's this total circle here is 52%. But again, you have that 7% in the middle that have done both. Okay, so you have to account for that. And then, of course, when it says that the 23% have taken the computer course, that includes 7% that have done both. So if we want to talk about the ones who have done neither statistics nor computer, okay, those are the ones who are not eligible for bioresearch. Then I want all this outside edge. In order to get all of this outside, I need to see what is in the middle there. So that's what I did here. So this is the general addition rule, where you are adding together one circle plus the other circle, because if I add all the stats plus all the computer, then see that middle gets double counted. That's why that got subtracted. And so then whenever you have that, that totals up to 68%. So this total amount of students who have had all this in the middle that have had stats and or computer is 68%. So the rest is 32%, 1 minus that. All right, so what's the probability that this junior biology major who has taken statistics? So that is the given that they've taken statistics. So out of the 52% who have taken statistics, what is the computer and statistics intersection portion? So if I was to take a look at this picture that I have, that is essentially what that's saying is out of this entire circle that contains 0.52, what portion is this section here? The 7% of the 52. So that's how you get that 0.1346. All right. And so then similar type question, just worded differently so you could see that. What's the probability that a junior biology major who has taken a computer course? So that's given that they've taken computer. So out of the 23%, who's the computer? 7% have taken both. Now, are they disjoint? Well, disjoint means have no outcomes in common. That would be a circle that are completely separated from each other. And so this is not, obviously. Okay. The dogs are barking, okay? So, Addie, hush. Go outside. Go outside. Okay, so disjoint. Okay, so these are joint, obviously, because they've got some that have had both. This is what disjoint would look like. All right? I had closed the front door so that the dogs wouldn't do that, because I figure this evening there'd be some people walking and the dogs would want to bark at that, but they still did it anyway. Okay. Now, here's a problem that you really have to read carefully what they're saying so you can visualize what all the different parts are. Now, remember that our techniques are to either do, this Venn diagram here, but some people want to do the two-way table. And so either one of these are going to take care of what you need. So it's, your personal preference. What are you visualizing? Okay, so you can see this 40% corresponds there. Here is the ones that have a dog but no cat. That's right there. Okay, and then here are the ones that have a cat but no dog. That's right there. And then, of course, here's the ones that have both. All right, so see, whatever works for you, whichever is your best way to visualize that. So here, we were told, that we had that 39% own at least one dog. So that means this here total for the dog yeses is 0.39. 34% own at least one cat. So then that's telling me this right here. But it is known that 60% own a cat or a dog. So that means that these three little parts right here that add together have to total up, well, everything but this has to total up to that 60%. And so then that's whenever we have the different parts there that you can do the 7. If I know that the 0.34 plus the 0.39 is 0.73. Okay, so the total of the cat and the dog is that 0.73, but then I'm going to be taking away the part that gets overlapped. All right, so then the yes part is the 13%. Next, so based on the survey results, what proportion of the U.S. households own neither? Okay, so then that's finding this outside part here, that 40% that do not own either. Are they disjoint? Well, nope, we can see right there. They are joint because 13% own both. All right, now here is a very commonly missed problem. This is one of the very common ones that I see missed on the quiz whenever we do this unit. So it says, what's the probability that a randomly selected household owns a cat if it is known that they have a dog? So that's this, given that they have a dog, what's the probability they have a cat? And I'm telling you, inevitably, the type of answers that I get are 0.34. This is the most common wrong answer. They put the cat portion over the dog portion. And they say, oh, probability of cat over probability of dog. That's not what the formula says. Because in this 34%, there's some of them, there's 21% that, look, in that cat circle, 21% of them don't have a dog. So when you're saying, given that they have a dog, then that's saying, hey, out of this whole entire dog circle here, out of that total 39%, what portion of that 39%, so don't you be counting that 21% over there of cat only. No. Of that, who also owns a cat? And that's that little section there. So that's the 0.13 out of the total 0.39. All right. Biggest, most common mistake. All right. And then what's the probability that a randomly selected U.S. household owns a cat? So out of the cat ones. This one usually is more commonly correct because people don't think about putting 0.39 over 0.34. So that one doesn't come out wrong as frequently as question D. All right, moving on. Next, here we have a big old tree diagram. So the reason that I knew that it was a big old tree diagram is because I read multiple conditional probabilities. If the computer chips from company A, then it's this defective rate. If the computer chip is from company B, then it is this defective rate. And finally, if it's from company C, here's even a third defective rate. So it was multiple conditional probabilities upon being from a particular company. All right. So that is why I said to myself, hey, self, multiple conditional probabilities. Oh, a tree diagram is the strategy for me. So I organized it that way. So I came out here and I said, okay, we got the manufacturing. And then they told us that this is the proportion that came from company A, from B, and C. And then from those, you go off of, if given that they're from A, this is the defective rate. Given that they're from B, here's the defective rate, and given they're from C. Now watch this. It said 0.5%. That's 0.005. So that's another common error in this particular problem. So watch that there. So then we know, so see, look, this right here. This is defective and from company A. Here is defective and from company B and defective. And here is from company C and defective. So what I have here in orange are the total ways, the total proportion of all the chips that are defective. So when the question is asked, given that they discover a computer chip that is defective. So given that it's defective, so that's out of these 3 pieces, total that up to get the defective total. And so see, that's me adding those pieces together. What proportion of that, or what piece of that is the company B portion? Well, that's this little guy right here. So that's why that's the numerator. So the denominator will be the total of those. And the numerator will always be a part of the whole in the bottom. Okay, moving on. And so then that's how we got the percent, whatever that was, the 0.347 something. Okay, what's the probability that a randomly selected student, so out of all the students, okay, so we're watching our denominators carefully here. The female ones is the numerator. So that's what you got there. And then here, what's the probability that a randomly selected student is a female? So again, if it is known that the student ate breakfast, so that's you're given that right here. All right. And so then upon learning the student ate breakfast, so that's again, given that the student ate breakfast, what's the probability the student is a female? So that was just another way of wording the same question. All right, now, here we have the question about, are these events independent? You could also say, are they related? Is there an association between gender? Okay, so those are other words they could have asked, and you would do the same thing here. So we know that we must check this particular situation right here. That is the requirement for the check on this. We have to say, hey, what's the probability of A? Okay, overall, what's the probability of A? And then what's the probability of A given B? Is the fact that B has happened, did it change the rate at which A occurred? Well, let's see. Now, I kind of went, you actually could do this several different ways, okay? You could do being a female eating breakfast. You could do being a male eating breakfast. Pick one of the genders, okay? And then pick eating breakfast or not. Now, the way I chose to do it, because I wanted it to make sense to myself, is I thought, okay, what's kind of the explanatory variable? And so I actually don't like the way that I did this problem here, because kind of the way I did this problem is I said, hey, if I know you have had breakfast, then what's the probability you were a female? So that's interesting. I guess I did that. So I did that because I happened to already know this right here from parts B and C. So apparently I went with that. So this kind of was the driver as to why I just used that. And I said, okay, that's the rate at which if you ate breakfast, this is the probability you're a female, but then here's the female overall. So this is the marginal, and this is conditional upon you having eaten breakfast. Now, look here. If it wasn't for the fact that I had already had one of those conditional probabilities done, I think it would have made more sense, really, in the real world to have done something like this. Given that you are a female, at what rate do you eat breakfast? Okay? And see if the fact that you're a female changes the rate at which you eat breakfast from the breakfast rate overall. So, eating breakfast, given that you're a female. So, you would find out those two probabilities and see if the fact that you're a female, given that you're a female, did it change the probability you have eaten breakfast? Okay. So there's what's going on with that couple. So you really have options of how you could have mathematically done this, but regardless of which way, you showed that they are not independent. Now, remember that these need to be within 1 percentage point. So this is 60.1%. This is 65.5%. So they need to be within 1 percentage point. Here's an example, like if you ended up with 32.5%, and say 33.1%, okay, because of the way fractions fall, that could have happened. That's within 1 percentage point, okay, so that could be as close as the fractions will get. Sounds like the dogs are getting ready to bark again. So here we go, moving on. Number 5. So I see we have this probability of at least 1. So remember, there's lots of different ways that this can happen. So the probability of at least 1 is right here, 1 minus the probability that none of those 4 motorists are going over 5 miles over the speed limit. So that's 1 minus the probability that all 4 of them are not speeding. Well, 40% is speeding, right? Yeah, 40% are considered the speeding. So 4 are not speeding is that right there. And we do 1 minus the probability of none. That will get everything 1 and above if you do 1 minus the nones. All right. Here we have again, okay, and so I remember also this was an actual AP multiple choice question, okay? So let's take a look at this. When they say 17% of students are enrolled in psychology course, so that's this total amount. Do you see this green here? This is the total amount right here in the psychology course, that whole circle. And 28% are enrolled in a foreign language. So that's the whole circle. Well, there's double counted in the middle there. And it says that it should total to 32%. So what that tells me is that, okay, if I added 28 plus 17, I need to take away the part that gets double counted, and then I will get a total of 32. So here is the double counted part, okay? And so that's what I'm showing here also. 28, the foreign language part, plus the psychology part, minus the part that gets double counted, should total 32%. Okay, so there you go. All right, number 7. Eye color and gender are independent. So that means if you know the rate at which males have brown eyes, then you know that the females will be the same rate. So I can tell that, again, 75% of the males have brown eyes. So then you set that female rate to the same. So make it so 75% of the females have brown eyes. If there were 80 males of the 200 students, then 120 were females. So I did 75% of the 120. And that's how I get 90. All right, so this is a very interesting problem. You really, to do this, have to know those definitions of that mutually exclusive. This is an actual AP question. So notice they use the words mutually exclusive. How do we think of that as mutually exclusive? The vocabulary we've used some, disjoint. So mutually exclusive from each other. Exclusive, completely separate, not joint. Okay, so you really have to know that definition of what that means and independence, what that definition means. So let's talk through this. So the probability of being awarded the first job, so event A is this. The probability of being awarded the second job is this. The probability of being awarded both jobs is this. So what if there is independence? Then the probability of A times the probability of B. So the fact that you are one thing, it's not changing. If they're independent, then that would equal this, the probability of A and B. So what I'm going to do then is multiply 0.75 times 0.5 and see if that gets me 0.375. And it does. So 0.75 times 0.5 does equal 0.375. So I know they are independent. So I do know that. But the question is about, so they are independent. So they are independent. So they are independent. All right. So now I'm down to A or C. So I need to know, are they mutually exclusive? Are they joint or disjoint? Well, hello. There are some that are both. That means there is overlap. So they are joint. They are not disjoint. They are not mutually exclusive. So that's why that answer is C. So this problem was a total, do you know the definitions of the independent mathematically and mutually exclusive being the same as your disjoint? All right, number 9. So this again, we have been told the total about the dog probability and the total about the cat probability. But then the question is, what's the probability that a selected household will own a dog or a cat? Well, the issue is this, see, for the general addition rule. Now, if my events were disjoint and nobody owned a dog and a cat, then I could just add those probabilities together. But obviously, that is not the case in real life. There is overlap for cat and dog. So that means if I just added the cat probability plus the dog probability, then I would have counted this piece twice. And so that's the missing information as to why I do not have the ability to answer this question. All right, and the final one. So here we have for A, B, and C, respectively, the probability of the failure for those components. So the question is, if any one component fails, then the device will fail. So if they are independent of each other, so one happening is not changing the probability, I could just multiply those together to get the total, okay? What's the probability the device will not fail? So here I wrote this out. For the device to not fail, all three successes or all three components must be good. So what that tells me is A has to be good and B has to be good and C has to be good. So then I took those pieces 0.99 plus times 0.97 because that and times 0.96. And so that's how you get that total probability of not failing because they all had to be successful. All right. So hopefully you followed that logic and that you did okay on these because there was just 10 questions here. Now some of them were multiple parts, but very important that you remember these basic probability components. All right. So next, we'll go on to geometric probability and binomial probability.